So I am Professor Anil Verma from the Department of Chemical Engineering at IIT Delhi. As we all know that global warming is one of the biggest problems of the earth because of the excessive utilization of fossil fuel derived energy. Therefore, I'll discuss about an energy storage and conversion technology which can be used for a wide application such as charging a station for electric vehicle, commercial power backups, rural electrification and replacement to diesel generator. We can see that in very recent events, the diesel generators in the National Capital Territory, Delhi, were banned because of emissions generated by diesel generators. Further, since there is currently no potential alternative to DG and hence as a temporary measure, the controlling authorities asked to install emission control device in the DG. To address such alarming global warming and air pollution situation, the nations across the globe are putting collective efforts for promoting the uses of renewable energy. India has also committed in COP26, which was held in Glasgow, that it will increase the non-fossil fuel generation to 500 gigawatt by 2030. And net carbon emissions would be cut by 1 billion tons, and also to achieve target of net zero emission by 2070. Considering the targets to be quite ambitious, it is believed that these targets may be achieved if alternatives to fossil fuel based technologies and aggressive focus on development of such a battery which can store large amount of renewable energy and capable of delivering uninterrupted power for long duration. Here, we are considering power backup to telecom tower for its efficient functioning. Because the primary power backup of telecom tower is by diesel generators, these DGs typically operate for around 2 to 12 hours a day, and the backup time typically varies with the state of geographical location. For example, in urban areas 2 to 4 hours and in rural areas 6 to 12 hours a day. Power backup is required in India for telecom tower functioning. India has second largest telecom market in the world with around 6.5 lakh telecom towers at a growth rate of around 7%. Due to the large dependency on the DG, the process of power backup for telecom industry has become non-eco-friendly, expensive as well as inefficient also. With these problems in picture, it is quite inevitable that replacement of DG is required with suitable battery. We have developed vanadium redox flow battery which is suitable for such applications. The vanadium redox flow battery is an electrochemical storage and conversion device that utilizes the ability of vanadium ions to exist in different oxidation states. It uses vanadium containing liquid electrolytes in tanks to store and utilize renewable energy via electrochemical reactions in a stack. During charging, the electrical energy from renewable source or even from the grid can be stored in the liquid electrolyte, and during discharging, the stored energy can be utilized for a variety of applications. The key features of this technology are its independent scaling of energy and power capacity, high cycle life, high operational efficiencies, deep discharge and the charge capability, and non-hazardous operation. If we compare the commercial lead-acid battery, lithium-ion battery as well as diesel generator with the VRFB, it can be seen that VRFB is quite competitive in all the fronts as well as suitable for large-scale renewable energy storage and for long duration power backups. Moreover, the levelized cost of energy of the technology is lowest, right? So, now you can see the quantitative data that how VRFB is better option than the diesel generator. It can be seen that for a single DG for one telecom tower produces more than 57,000 kg of CO2 and also costing double the cost of VRFB. We are working on VRFB technology from last 7 years. Let's see the evolution and innovation status. So we have been working on the VRFB technology since 2014. At the beginning, we worked on fundamental aspects of VRFB, and during that phase, we could successfully able to understand the dynamics and science behind a single cell of VRFB. In 2017, our lab generated significant know-how about the technology, and by this state, the lab started to file patents on different aspects of the technology. By 2019, the lab was successfully able to design and develop the first working prototype of VRFB that had a power rating of around 6 watt, and we filed a few more patents. Development of a smart electrolyte health management system and development of 3 times more efficient electrode, etc. Now, carrying on with the confidence, the lab has recently developed and demonstrated a prototype of a charging station which is installed in IIT Delhi and inaugurated by the director IIT Delhi. This VRFB based charging station prototype is capable to charge the personal gadgets, all kind of personal gadgets in fact. So, we are presently developing VRFB system for telecom tower and for electric vehicle charging station. So we have tie-up with the telecom industry for developing VRFB system to replace DG. Further, we have got funding from FIRE scheme of IIT Delhi to develop the electric vehicle charging station in the campus. Okay, with all the effort of work being put together along with the funding, especially from the DST, the technology from our lab stands at the TRL 7. Right. So, motivated by the intensity of work carried by the lab, the team has incorporated a company which is a startup company named AWAT Technologies Private Limited. Our effort is in line with the nation's COP26 commitment. So, recently our group, in collaboration with AWAT Technologies Private Limited, has been selected to deploy the battery under DST's call on National Innovation Challenge Award for designing and developing energy storage devices for rural household or enterprise applications. So with that, I would like to acknowledge my students, staff members, funding agencies and IIT Delhi for the support. With that, I would like to thank everybody. So we have developed a charging station which is based on the vanadium redox flow battery. So in this particular flow battery, anybody can charge his mobile, laptop and other personal gadgets, and it can give the backup of around 9 to 10 hours. And the capacity of or the power of this the battery which is kept in this station is half a kilowatt. So in this particular charging station, we have the vanadium redox flow battery. So this vanadium redox flow battery has two things. One is the electrolyte, another is the stack. So what we do, we pump the electrolyte into the stack so that we can get the energy. So that energy or the electricity is utilized to charge the laptop, mobile phones or other personal gadgets. So this is basically, if you see, there is no pollution in this particular technology because it is a kind of battery, and this battery has a different structure. What we use presently, we have a solid state battery, but here the battery is the liquid state battery, where if we want, we can increase the energy capacity independently and we can also increase the power capacity of the battery. So in a way, this is similar to the diesel generator, but here we are not polluting the environment, we are not generating any carbon dioxide, and it is environment friendly. So this technology we have patented. We have in fact patented 7 patents, national and international patents. And we have also formed a company named the AWAT Technologies Private Limited, and we are also in collaboration with various industries. We are trying to develop the system so that we can replace the diesel generator. At the same time, we can provide the solution to charge the electric vehicle using this charging station.
This is a vanadium redox flow battery demonstration rig. In this particular test rig, we are testing a 150 watt VRFB stack. Moreover, we are also working upon the battery management system components as well as the power electronic components that are required to run this system. This is a state-of-the-art Arbin testing equipment. Here we have the capability to test VRFBs up to 2 kilowatt range, and these two are indigenously developed VRFB single cells.
This is the same setup that we saw at the charging station earlier. So here we have a 500 watt VRFB stack. These are the pumps that deliver the electrolyte from these tanks to the stack, and the reactions happen. So at the negative side we have the V2 plus and V3 plus electrolytes, and at the positive side we have the V4 plus and V5 plus electrolytes. Next, we are working on the development of a state-of-the-art 5 kilowatt VRFB stack that is very compact as compared to the design we saw earlier.